Hi everyone, this is Charan Sisavarma. Today I was going to explain about Turing machine. First, I want to give introduction about Turing machine. Turing machine was first discovered by Alan Turing in 1936. It is simple abstract computational device which intended to help investigate the extent and limitations of what can be computed, specifically devised for the computing of real numbers. They were first named Turing machines by Along Church in a review of Turing's paper. Today, they're considered to be one of the foundational models of computability and theoretical computer science. Visualization of a tape. Turing machines were very simple to visualize. It can be visualized as a single one-dimensional array of cells, each of which can hold a single symbol. This array extends indefinitely in both directions and is therefore capable of holding an unlimited amount of information. The information can be read and changed in any order. They are called tapes because it is analogous to the magnetic tapes used in older computers. The definition of a Turing machine. A Turing machine is an automaton whose temporary storage is a tape. This tape is divided into cells, each of which is capable of holding one symbol. Turing machines are associated with the tape is a red bright head that can travel right or left on the tape and that can read and write a single symbol on each move. This is the representation of a Turing machine. Here we can see control unit, read write head and tape. Turing machine is M is defined by a 7 tuple M. In the 7 tuple contains Q, sigma and table alphabet, transition function and blank symbol. Here Q is set of internal states and sigma is input alphabet and the table alphabet is a finite set of symbols and sigma is the transition function and B is the blank symbol. Q naught is the initial state and F is a set of final states. A simple Turing machine would look like this, a tape and a read or write head. Now we can compare the Turing machine with other automation. The following table shows a comparison of how a Turing machine differs from finite automaton and push-down automaton. Here we can see stacked data structure and deterministic differences in between finite automaton, push-down automaton, and Turing machine. In finite automaton, the stack data structure is NA and it is deterministic, whereas in push-down automaton, it is last in first out and non-deterministic. Here we can see Turing machine has infinite tape in stack data structure and also deterministic. Example of a Turing machine. We can consider this example for Turing machine. If this Turing machine is started in state Q0 with the symbol A under the read write head, the applicable transition rule is delta of Q0 comma A equals to Q0 comma B comma capital R. Therefore, the read write head will replace the A with AB. Then move right on the tape. The machine will remain in state Q0. Any subsequent A will also be replaced with A, but AB, but B's will not be modified. When the machine encounters the first blank, it will move left one cell, then halt in the final state Q1. Design. Designing of a Turing machine. Design a Turing machine that reads a string representing a binary number and erases all leading zeros in the string. However, if the string compromises of only zeros, it keeps one. Let us assume that the input string is terminated by a blank B at each end of the string. The Turing machine M can be constructed by the following moves. Let Q0 be the initial state. If M is in Q0 on reading 0, it moves right and enters the state Q1 and erases 0. On reading 1, it enters the state Q2 and moves right. If M is in Q1 on reading 0, it moves right and erases 0. It replaces by zeros by B's. On reaching the leftmost one, it enters Q2 and moves right. If it reaches B, the string compromises of only zeros. It moves left and enters the state Q3. Then, if M2 is in Q2, on reading either 0 or 1, it moves right. On reaching B, it moves left and enters the state Q4. It validates that the string compromises of only zeros and ones. If M is in Q3, it replaces by B or by 0. moves left and reaches the final state QF. If M is in Q4 or reading either 0 or 1, it moves left. On reaching the beginning of the string, when it reads B, it reaches the final state QF. Hence, the result will be M equals to set of Q0, Q1, Q2, Q3, Q4, QF. And the remaining set will be 0, 1B and 1B and sigma Q0 B, comma Q final state. And we can see the result in the PPT given. Designing a Turing machine in the table format will be easy to understand. Here the transition 1 RQ1 implies that the right symbol is 1. The tape moves right and the next state is Q1. Similarly, the transition 1 LQ2 implies that the right symbol is 1. The tape moves left and the next state is Q2. Here we can understand that we can easily understand a Turing machine by representing them in a table format. And we also should know the applications of Turing machine. Applications of Turing machines. Today, the Turing machine and its theory are part of theoretical foundations of computers. It is a standard reference in research of foundational questions such as what is algorithm, what is computation, what is physical computation, what is an efficient computation, like etc. Now, we can see some applications in some examples. For solving any recursively enumerable problem, we should use the application. A recursively enumerable language is a formal language for which there exists a Turing machine or any other computable function that will halt and accept when presented with any string in the language as input, but may either halt and reject or loop forever when presented with a string not in the language. Contrast these two recursive languages which require that the Turing machine halts in all cases. For understanding complexity theory, computational complexity theory is a subfield of theoretical computer science, one of whose primary goals is to classify and compare the practical difficulty of solving problems about finite combinational objects. And for implementation of neural networks. Neural networks are set of algorithms modeled loosely after the human brain that are designed to recognize patterns. These neural networks can be implemented digitally by using a special kind of Turing machine called neural Turing machine. Such neural networks are called artificial neural networks. For implementation of robotic applications, robot takes place in a lot of information for the surrounding, process those information and use it to do their intent operation. Turing machine being a computational model helps to solve complex problems that may arise during the operation of the robot. For implementation of artificial intelligence, the aim of neural Turing machine is to design a computational model which can fulfill the objectives of AI by designing learning algorithms that can be work such as the brain of the human. The new neural learning technology in artificial intelligence is called as deep learning, which tries to manage the cognitive problems and provides a system where human brain like pattern can be observed. NTMs. NTMs are also greatest discovery which contributed a lot towards machine learning. It opens the various options by which machine learning can be used to learn various algorithms which can access external memory. Here, there are many applications for the Turing machine, and I'm giving some links to understand more about the Turing machine here in this PPT. Thank you for giving this opportunity.